Okay, one more thing. Those who have missed a class test for a valid reason, you have mailed me before. Please forward your mail again. I will give only for those. I will give a date and time for a makeup. Only one makeup is possible. But for those who have mailed earlier, just forward that mail to me. I will give you a date and time to appear. Okay. And one more thing, I think you have noticed, I have increased your homework to submission date up to Thursday. So I have added 5 more days, but please remember, don't copy. Don't copy. Do it yourself. Whatever you can do, that will help you in the final exam. So I have extended the time. Many of you requested me. I expect nobody will copy. Okay. Okay. So
Sir,
yes,
let me ask you a
If we
question from the
discuss,
quiz.
yes.
Sir, in the fragmentation question, the 3000 datagram of 3000 bytes and frames of maximum 1200 bytes.
Yes.
Sir, what will be the correct answer? 600 or 620?
I have to see. I am not sure. Just after 1 p.m. today, after 1 p.m., you will get the details. Okay.
Okay, sir.
Because now it is blocked because there is another exam in section B. So that's why after 1 if you don't get the feedback active, just send me an email. I will if in case I forget, then I will make it on, and then you will get the answer. And then if you have any question, you can mail me. Okay. Okay, so let us go back to the part that we have finished in the last class, that is up to slide number 8. We have finished.
So আমাদের সেটি কি 3টা কাউন্ট হবে?
Sorry, yes, 3 out of 5. 3 out of 5. So this was the last slide we have covered. We have covered the basic data link layer concepts. And then let us start from here today. I think I did not share, right? So I have to
Yes, sir.
share screen. Okay. Okay, so this is section 6.3 that mainly talks about multiple access links and protocols. So you can remember we said one of the services data link layer provides is link access. That means how many devices, how different devices can access the link. If you can see the pictures here, you can see shared wire, cable Ethernet. It is actually old technology of Ethernet. It was called bus technology, but now we use hub or switch. But the idea is, if you use hub, the idea is same. There is a common shared wire where everybody transmits. But if more than one transmits, then there is a collision. I think you have seen that in the network lab, right? So in case of collision, the entire frame is damaged. So the sender must retransmit the entire frame. So that is one option. Then fourth generation, fifth generation, we already use 4G, right? 3G, 4G. So in that case, there is a base station, and then the mobile nodes share the common radio spectrum among themselves, like we use our mobile phone for voice. Then there is another example of shared radio is Wi-Fi. You know how Wi-Fi works? When we configure a wireless router, actually there is a difference between mobile 4G or 3G with the Wi-Fi, because in Wi-Fi there are 11 channels in the wireless router, but one channel you can use at a time. So all the nodes using Wi-Fi, they use a one shared channel. That means actually at a particular time, one communication is taking place. But wireless router communicates that, so multiple communications can happen at the same time, but theoretically, at a particular time, only one communication happens because there is a single channel shared. So that is Wi-Fi. Then satellite. You know, satellite, there is a transmitter, there are different receivers like satellite dish and satellite internet, like other things. So one common uh, 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 machine that actually receives and transmits, mainly transmits, and there can be receivers in the on the earth. So multiple receivers can receive. So this is another uh, idea of link access. And if you want to just get a real life example, now I am talking over the internet. So I am talking, you are all muted. So this is one kind of multiple access. All are listening to me. But if I give the floor open, then you can talk, I can listen, or many can talk. Multiple of you have mic unmuted. Then what will happen? The noise will happen, right? Interference will happen. So what we do, we try to get a protocol so that one can speak and others can listen. In that case, the communication is more efficient. So the example is like a human at a cocktail party or in a program where there are shared air, but there are smaller groups. Some people are talking somewhere, some people is talking in another place, not close to each other. So if we change the tone, if I increase or decrease the power of the voice, then still communication can happen. So all these examples are examples of how we can give access to a shared media. So based on that, there are two types of links. One is point to point. Point to point means there are two nodes connected. For example, a PC connected to switch, then two routers interconnected. So there is no sharing, you can see. One transmits, another one receives. So that is point to point. Okay. Then second example, second category is broadcast. We have given some examples of actually broadcast. Shared wire or media. That is old-fashioned Ethernet, first diagram. Or you can think about the dish connectivity, cable-based access network, hybrid fiber coaxial. We have read in chapter 1. Through the dish connection, we can also send data. So that is possible. And then Wi-Fi, very common, 802.11 wireless LAN, that is a Wi-Fi. Then mobile, 4G, 3G, then satellite. These are all examples of where shared media will be used by all. Now, how we can give, how the protocols can be categorized based on the characteristics. So based on that, multiple access protocols can be categorized into different categories. Before that, let us know more about multiple access protocol. Again, it means there is a single shared broadcast channel and multiple nodes will access that channel. So we know if two or more simultaneous transmissions in the same line, same channel, definitely there is a collision. That is interference between the signals. So the original signal will not be there. That is called collision. And whenever a collision happens, actually we need to retransmit because the entire frame is damaged. So what is the idea of multiple access protocol? It's a distributed algorithm that determines how nodes share channel. We'll see different examples shortly. Determine when node can transmit so that maybe collision will not be there. There is no possibility of collision. Or in some cases, if still collision can happen, interference can happen, then we have to have some mechanism so that how we can overcome that collision. That means how we can transfer that particular packet successfully in some time. So multiple access protocol or algorithm actually gives us that solution. And in this case, communication about channel sharing must use the channel itself. So in any protocol you use in networking, you have to keep in mind whatever extra message we exchange, like the control messages we exchange, in networking there is no separate channel. The same line, the same media is used, so no out of band channel for coordination. So there is a trade-off. If you use coordination, the possibility of collision and interference will be less, right? Or no possibility. But if we use coordination, then you have to use extra bandwidth because you have to coordinate among the nodes. So in that case, more bandwidth will be needed. So there is a trade-off. Based on that, we can categorize all protocols in multiple access control into three broad classes. First one, channel partitioning. I think already we have got an idea about channel partitioning in chapter 1 when you read CDMA, TDMA, FDMA, right? Frequency division, time division, where the entire shared channel is divided into smaller pieces. That can be a time slot, that can be a frequency range, that can be a separate code for separate users. This is mostly the topic of mobile cellular communication. We will not go to in depth of that concept here in this course, but you can get, okay, in case of channel partitioning, since there are smaller pieces and one piece, or more pieces are allocated to a node for exclusive use. That means that piece of info, that piece of time slot or frequency will not be shared with others. So what is the advantage of channel partitioning? The advantage is there is no collision, right? What can be the disadvantage? Anyone? What can be a disadvantage here? If we divide the channel into smaller pieces and give one piece to each user for exclusive use, that means when the user uses that piece, nobody will be allowed to, even if the user is inactive at a particular time. What will be disadvantage? Inefficiency, right? Utilization might be less. I think we have already mentioned this in chapter 1, because these are examples of circuit switching normally. So circuit switching has less utilization. Why? Because of this. Then second category is random access, channel not divided. So there is no coordination. There is no division of channels. What is the outcome? This is actually example of packet switching. So where a packet is transmitted through a link, the entire bandwidth is used by the packet. There is no division of bandwidth. So what can happen here? Anytime, any node, anytime can transmit packets. So definitely collision can happen. You cannot avoid collision because there is no coordination. But if collision happens, you have to have a mechanism to recover from collision. So random access protocols actually do that. And the last category is taking turns. You know, when we have played cricket, right? At the earlier age, we played cricket. Okay, we have given numbering, right? And then you have to choose your number. So 1, 2, 3, 4, 5, 6. So I have chosen 5. So I will be at serial number 5. I will bat at number 5. So taking turns, no collision. Otherwise, what will happen? 2 or more will say, okay, I will bet now. Similarly, 2 or more nodes will say, I will send now. So to remove that, there is a mechanism to numbering the nodes so that there will be no collision and interference. So in this taking turns also there will be no collision. That is advantage. But the disadvantage again is, since there is a numbering scheme, so even if a node has data to transmit, the nodes need to wait longer amount of time because it must go around every node, those who have data to send and also those who don't have data to send, and then it will come back again. So that's the idea of taking turns, and these type of protocols are obsolete almost now. And you will be interestingly, you will know that The random access protocol, where any node can transfer any time, collision can happen, this gives the best performance in local area networks. So we will read something about Ethernet, some protocols about Ethernet. Ethernet is a wired LAN protocol, and Ethernet uses a random access protocol. No channel partitioning, no taking turns. Clear? Any question? Now, if you go back, I think we have seen this example in chapter 1 also, TDMA. The entire time is divided into smaller slots, and then in this example there are 6 slot frame. You can see 1, 3, 4, and then when a slot is assigned to user 1 or user 3 or user 4, no one else can use that slot, even if the user is idle for some time. Similarly, frequency can be divided. Then random access, as I said, when node has packet to send, data to send, transmit at full channel data rate R. So if the capacity is R, a node will use the entire capacity, and there is no a priori coordination among the nodes. No possibility of coordination. So no coordination means actually more efficient, because there is no extra bandwidth needed. But the problem is when 2 or more transmitting nodes, there is a collision, and a random access MAC protocol like CSMA CD, CSMA, I think maybe in data communication course or some other course you have covered this type of protocols. Did you study CSMA in some other course? Carrier sense multiple access. And then there are some was it covered in data communication course? Anybody?
We didn't do it.
Okay, I think there are some protocols for random access. Okay, anyway, we will cover one here. But any random access MAC protocol specifies, first thing, definitely collision can happen here. So you cannot avoid collision because there is no coordination. But protocol must specify how to detect the collisions. And if the collision is detected, the second part is how to recover from collision. That means, you know, if collision happened, the entire frame is damaged. So you have to retransmit the entire frame again. Even if some part of the frame is damaged, signals collided or interference, got interference, entire frame must be retransmitted. So that must be taken care of by any random access protocol. Okay, these are the examples: Aloha, slotted Aloha, CSMA, CSMA CD, CSMA CA. All these protocols are random access protocols. So Aloha is the very primitive protocol. Then slotted Aloha, and we will try to cover CSMA CD. Although this is very little need of this in case of wired network. Now, okay, we will cover CSMA. Okay, let us go forward. CSMA is carrier sense multiple access. So carrier sense means what? Carrier sense means actually in random access protocol, as we said, any node can transmit any time. So if more than one nodes transmit the shared medium, then there is a collision. So what simple CSMA says, to reduce the collision, every node must listen to the channel. So if the channel is sensed idle, only then transmit. If the channel is sensed busy, no, I cannot transmit. I have to defer. Defer means I have to wait until the channel becomes idle. Okay, but whenever it starts transmit, it starts transmitting the entire frame. You know, a frame is, for example, we have seen that MTU, maximum transferable unit, that is the property of data link layer. So in data link layer, for example, a packet has 1500 bytes. So 1500 bytes means 1500 into 8 bits. each bit is converted to signal. So there must be a time needed. Probably that is T frame. So that amount of time needed to transmit the entire frame. For example, that is 10 millisecond. For example, in that 10 millisecond, in any part of that transmission, if that collides with any other signals of other nodes, then we call that a collision. Okay, so if the channel is sensed idle, only then it transmits. And the human analogy is actually don't interrupt others. So if someone is transmitting, let it be finished before I can transmit. So normally it seems that collision will not happen, right? But collision can still happen because of that propagation delay. So CSMA, even we sense the carrier before transmission, still collision can happen. So CSMA CD, in case of basic CSMA, if collision happens, still it continues to the transmission, and then the frame is damaged and then retransmits. In case of CSMA CD, it adds an extra mechanism, that is collision detection. Why? If it transmits the collision, if it transmits and detects the collision, then after the collision is detected, as early as possible the collision is detected, transmission stops, because rest of the frame transmission will be wastage. As I said, if some part collided, entire frame will be damaged. So if I already transmitted like 500 bytes, but I have still 900 bytes, a collision happened, sending 900 bytes will be wastage. So stop there, and then that will reduce the channel wastage. Okay, and then there will be the part of retransmission, calculation for the retransmission. We'll see in an example. But collision detection is easy in wired LAN, and collision detection is difficult in wireless LAN, because you know in wireless LAN transmitting power is much higher than the receiving power. So there is a difference. So in the circuitry, in the hardware, that is not feasible to implement collision detection in wireless networks. That's why wireless networks use collision avoidance. Okay, CSMA-CA. CA means collision avoidance. Okay, third category, taking turns. And this type of category has example. One example is polling. Polling means there is a master node, there is a coordinator. Like master node will number the slave nodes 1, 2, 3, 4, right? And then typically the slave nodes are dumb. Dumb means whatever they are instructed to, they will do. So in that case, master will number, and then master will ask one by one to do something or to send data. So this is the idea. But again, there is some overhead involved here, because master node will coordinate, delay will be more, and also if master node fails, the entire mechanism fails. So this is the problem with polling, like this. Okay, so master says, okay, send you data, this sending, then says, okay, send you data. So master node will always coordinate who will send, but that coordination will add overhead. Another mechanism in taking turns is token passing. There is a token, you can see, and that token will move. Okay, so whenever there are some data, the token will be filled up. But if a node has no data to send, it will just forward the token. But still, a node has no data to send, still the token will go through that node. That is the problem here. That is the latency or delay. Okay, and then there is a data. So this node will add the data to the box or token. Okay, like this. Again, this has the same problem. Single point of failure. If the token fails, then the system will not work. Overhead is there, and also delay is there. So this type of protocols actually almost obsolete now, not used anymore. So we will see an example of CSMA CD maybe in the next class. The next very, very important concept is what we call ARP, Address Resolution Protocol. and that is one of the important protocol in networking, and one of the important protocol also for security. Okay, why this protocol needs? Because we have already learned IP address, right? It's a layer 3 protocol. It's a network layer addressing or forwarding. And then we have also learned about the MAC address, right? Physical address. Why MAC was used? Used locally to get frame from one interface to another. Okay, so for physically connected interface. So we already, I think we know some idea about why MAC address is needed, because MAC address works within a segment, within a subnet. Okay, and IP address works all over the network. So that is the idea. And MAC address is 48-bit, burned into the network interface card. What is network interface card? Anybody? What is NIC? Can you tell me?
Sir, LAN card.
Right, LAN card. Very good. LAN card. So LAN card has a ROM. Okay, and you know, the program is burned into ROM, and that works. So that MAC address, 48-bit MAC address, actually burned into the ROM. Although in software we can change that, but it's actually built in the hardware. Sometimes software setable, but what is built in the hardware, that is the MAC address of that particular LAN card. Now, why I am saying this? Because I want to know about a protocol that is ARP, Address Resolution Protocol. Now you can think about an interface, very simple network. The network is a wired or wireless anyway. The network part is 137.196.7/24. That means that is the network address. And you can see all the PCs in this segment has a separate host part, like 78, then 14, then 23, then 88. You can see network address is same for all. And every node has a corresponding MAC address, right? Because this is a segment. Now, when we communicate, if we want to access a server, like server 16 at UIU, right? You have access server 16, 10.100.100.16. Can you remember when we did our physical classes? So we access that server. How you access that server? Anybody? Can you remember? You accessed a server 16. What was the IP address? 10.100.100.16. Can you remember? Did you access server 16?
No, sir.
No? How can we access server 16? Please tell me, anybody. I know the IP address, right? 10.100.100.16. Then how can I access? Mainul, can you tell me?
No, sir.
How can I access? I have just, we know the IP address is 10.100.100.16. How can I access that server from UIU network, not from home, from UIU network? Bador? Rajia, can anybody tell me?
Sir, can you repeat the question for one more time?
The question is, when we okay, it's a generic question. When we enter a server, right? We want to enter a server from anywhere in the network. We know the IP address of the server. How can we access the server? What are the ways? Using IP address, right? We can give the IP address in the run, Windows
Yes,
run.
sir.
We can give the IP address in the browser.
Yes, sir. I was
We
thinking
can,
about
right? That is what I was asking. We can give like facebook.com, google.com, but then that is converted to IP address.
we can add the URL as well.
Right, we can add the URL. So ultimately, even if you click somewhere, even if you give the domain name, ultimately it is converted to the IP address of the destination, right?
Yes, sir.
Yes.
Okay, so I think I have mentioned several times the same example, because that is the starting point of the network. If I ask the question, when network starts, when communication starts, when we give the IP address of the destination, right? So now assume this simple network. This simple network where 4 PCs are interconnected, maybe through a wireless router or through a hub or through a switch. Very simple network. If I want to communicate from 7.13 host to 7.14, how can I communicate? I have to give the destination IP, right? 137.196.7.14 from the source IP, 137.196.7.23 from this machine. Is it clear to everybody?
Yes.
Okay.
Yes, sir.
Now we are at data link layer. So we know, although we want to communicate, we want to transfer a file to a 7.14 host, or we want to copy a file from 7.14 host. So we go to Windows Run, or we go to different ways we can communicate with the IP. So as a user, I give the IP address of the destination. But now we know to transfer even a single frame to 7.14, the source needs what? The MAC address of 7.14. You got my point?
Yes.
Because without the destination MAC, we cannot create a frame. Whenever the source create a frame from the packet, it must give the source MAC as the source MAC address, right? Its own MAC as the source MAC address. And it must give the MAC address of the destination as the destination MAC address in the frame before it can transmit the frame. Is it clear or not?
Yes.
Yes, sir.
Okay. So the question is now, we know the IP address of the destination because user must know the IP address of the destination to start the communication. But as a user, we never give the MAC address of the destination to my PC, right? But to create the data frame, it must get the destination MAC. How that can be done? That is the question. Is the question clear? If the question is clear, then we'll understand what ARP is. So given the IP address of a destination, to create the data frame, the source needs to get also the MAC address of the destination corresponding to that IP address. How a sender can know that? Right? That is the question. As a user, we give the IP address, we don't give the MAC address. Any question? Is it clear? Mainul?
Clear.
Okay. So if the question is clear, then the concept will be very easy. We want to answer the question. What is the answer? The answer is the source will send a special packet that is called ARP, Address Resolution Protocol message. It will broadcast the network. So everybody will receive the message. What will be the message? The message will ask the question, okay, I know the destination IP 137.196.7.14, but I need to know the MAC address of that machine. So if you have this IP address, please send me your MAC address in reply. That is the simple idea. So that is how address resolution protocol works. See the question, how to determine the destination MAC address if I know the destination IP address. That is saying here. So as we said, 7.13 PC wants to send the data packet to 7.14, sorry, 7.23 PC wants to send a data packet to 7.14. Okay. And to do that, every node must create its own ARP table. ARP table means what? ARP table means every node will have these entries in the network. So IP address and then corresponding MAC address. And then there is a TTL value. TTL is how much time it will be in the table. But basically it's a mapping between IP address and MAC address. So if it needs to send a data to 7.14 physically, it needs to get the MAC address of 7.14. If that is not in the table, then ARP protocol will run. It will extract that MAC address and store in the table. You can give, let me show you command. Okay. So if I go to the command prompt, anytime I can see what is the ARP table in my machine right now. See, you can see there are different type of IP addresses. 192.168.0.1, 0.102. We don't know what are these IP addresses, but every address has a corresponding MAC address in my ARP table. So that is my okay. No, I think okay, you can give the command to your machine. I don't know how can I increase the font size here. Edit. Anyway, just you can give ARP-A command in your machine right now. You can give this, and then you will get a table where there are different IP addresses and then corresponding MAC addresses. How these addresses are got by this machine? See, ARP is not needed to be configured. Whenever you connect a machine to the network, it will internally run ARP by default. So after a certain amount of time, it will get the ARP table already. But we need to know how that is being done. So that's why every node has its own ARP table, but maybe ARP table is empty. Suppose assume this machine is just connected to the internet or just restarted. So it is empty. And then how this table actually filled up. Let us see. For example, A wants to send a datagram to B, and B's MAC address not in A's ARP table. Okay, so A uses ARP to find B's MAC address. Suppose A has no information about B's MAC address. So initially what A will do, see, table is empty. Suppose A has been shut down, restarted, or A has been just connected to the network. We don't need to configure it. Will internally run the ARP. How ARP will be run? Step 1. A broadcasts an ARP query containing B's IP address, because as a user we give the IP address. So A knows the IP address of B, but A needs to know the MAC address of B, right? So it will create a special message called ARP query where B's IP address will be given and the destination MAC address will be all F. All F means what? Any idea? Anybody? Actually, this is layer 2 broadcast. We know layer 3 broadcast. We know IP broadcast. What is IP broadcast? Can you tell me? What is the broadcast address in network layer? All ones in the host part, right?
Yes, sir.
All ones in the host part. Now that is in layer 3. That is IP. Now we are in data link layer. So you are using MAC. In the MAC address, if you give all ones, all 48 ones, that means in hexadecimal this is all F, right? Yes or no?
Yes, sir.
Yes. So this address represents the broadcast address in layer 2. That means whenever a switch, we know switch only sends data to the destination. Hub sends everywhere, but switch only sends to the destination. That is the advantage of switch. But whenever there is a frame with destination MAC all 1 in binary or all F in hexadecimal, that indicates this is a broadcast address. So switch will send that frame to everywhere. So in ARP query, since the source A doesn't know C, D, or B who has the 7.14 IP, it will broadcast to everybody. But then when they receive, all nodes on the LAN receive the query, when everybody receives the query, only node B will see, okay, this matches with my IP address, because target IP address is 7.14. So only the node with 7.14 IP will receive, C and D will discard. And then B will see, okay, I need to send my MAC address back to A. So B will reply with an ARP response where the MAC address will be given, and then A will update its table with the destination MAC of B. Clear? So this is the way how A knows the MAC address of B, and until this point A cannot convert a frame to signals, convert a data frame to signals. So using ARP, it knows the MAC address of B now, so it can create the data frame with source MAC of A, and destination MAC of B, and now it forwards the frame, converts to the signals. Is it clear?
Yes, sir. স্যার তার মানে কি স্যার আমি যে রাউটারের সাথে কানেক্টেড আমি চাইলে কি ওই রাউটারের সাথে যতগুলো কানেক্টেড আছে সবার ম্যাক অ্যাড্রেস জানতে পারবো?
Very good question. Who asked this? Mainul.
Yes, sir.
Very good. Very good. That is a very good question. Actually, we will see this because now how many servers Google has? Any idea? If not thousands, hundreds of servers, right?
Yes.
So we don't know maybe which LAN card is used by which server. That is possible for Google to advertise this MAC address of every LAN card of every server, but that is not feasible. So if we want to know the MAC address of a device beyond the network, that is not feasible. And fortunately, we have a very, very beautiful idea in networking that is called what? Default gateway. So default gateway makes this concept very easy. You will never need to know the MAC address beyond a segment, because see, this is a physical segment. So if we add router, physically the segments are separate. Router makes those physical segments separate, right?
Yes, sir.
So if I needed to know the MAC address beyond that segment, it would have been much more complex. But fortunately, we have default gateway. We never need to know any MAC address beyond that physical segment. How? Let me make that clear. So this is the example. This is the answer what Mainul has asked. But everybody should consider this, because the destination can be just connected with the same router. The destination can be after 100 routers. Okay? Because we have default gateway, we don't need to go beyond that default gateway. That is the beauty of this concept. So in this case, if B is in a different network, the router is in the middle, what needs to happen? Make it clear. In that case, actually we know what A will do. A will send the packet to B directly, or it will send the packet to router.
It will send packet to router.
Very good. Because the idea of default gateway is like this. Whenever destination is in a different network, the sender doesn't need to go to the destination. And actually, there is no way. The sender will transmit the packet to router. So in this case, doesn't matter. Destination is within connected to this router or destination is after 100 routers. Doesn't matter. You have the default gateway. So what you need to know? You need to know the MAC address of router. That's enough for A. A will hand over the frame to router, and routers will do the rest. Is the concept clear? Main concept. But now if I use this example, suppose again A needs to send a frame to B, but in this case we will see A will not need to know the MAC address of B. A will need to know the MAC address of router's port, because that is default gateway. So that is the idea. Let us see the example. So a frame packet has been created by network layer. Source IP is A, destination IP is B. Then data link layer needs to create a frame where it needs to get the source MAC is known, but the destination MAC will be what? Will it be the B's MAC, or it will need R's MAC? That is the question. Which one it needs? Router's MAC or B's MAC? Host B's
Router's MAC.
Yeah, router's MAC. So that is the idea. So you can see in the destination, the MAC address is of router's port, not the B's port. Why? Because of default gateway. I think all of we know what is default gateway. We need to configure IP address, subnet mask, and default gateway in a PC to be connected to the network. If you don't give the default gateway, it will not work beyond the network. Okay. So if that MAC address of router is not known to A, again it will use that ARP protocol. So if ARP runs, after the end of ARP protocol, it knows the MAC address of the router. Not only router, it knows the MAC address of all the nodes connected to A. Okay. And then what it will do? Send the frame to router. Then router's data link layer will do what? It will remove the header, and this is the packet. You can see The destination IP is needed by the router to forward the packet. Again, router will hand over its data link layer. Now the source MAC and destination MAC will be different. Now the source MAC will be the router's right side interface MAC, right? Is it clear? If you are clear the logic about the logic, then the value will be very simple. And the destination MAC, again, router is connected to B directly, physical connection. So router's data link layer will also run ARP to know the MAC address of B. In this example, we assume that ARP is already run. So MAC address is already known. So forwarded to B like this. Okay. And then finally, it will get the IP to the network layer. So throughout the journey, source IP, destination IP never changed, but the MAC address will change at every intermediate link. Is it clear?
Yes.
Anybody has any question? Okay, so we will do the last theoretical part. We have one last theoretical part on Monday. We have a makeup on Monday, and then we will do some hands-on examples on that day, and hopefully in the last class we can have some practice and we can discuss about the final exam syllabus. Okay, so let me stop here. If anybody has any question, I can answer, and by that time if you have any question, you can ask, and by that time let me take the attendance. Okay, anybody has any question? Okay, okay, please respond quickly. Okay, I am calling where is